Hello and welcome to our neural network tutorial. Today we are going to explore how to use R for neural networks. The topic I'm going to, the resource that I'm going to use today is from a paper published in the R journal, and it's the publishers are Frauke, Gunther, I think that was umlaut, and Stefan Fritsch. I'm sorry if I didn't pronounce your name correctly. It's a published paper in June 2010, and the name of the paper is neuralnet training of neural networks. So there they introduced a new package which is called neuralnet. So for you, in order for you to start, you just need to install this package neuralnet. So let me install it along you. So I just installed neuralnet. Okay. And then when you finish installing neuralnet, you need to require it, or just like library neuralnet. I just require neuralnet, and automatically when you require that function, two other classes or libraries will be read. One is greed, the other one is mass. You have used mass before when we used Boston data. In trees we used mass. We use this library a lot. So today we are going to work with a data set which is called infert. So let's see what is inside it. So this is a data set for infertility after spontaneous and induced abortion. So the data has two cases. So it has whether the case was infertile or if it was not. So it has control and cases. So the output where we have is called case status. If the case status is not infertile, that is 0, and if it is, that is 1. And you have a bunch of other variables like education, how many years of education that person had, the age of the person, and so on and so forth. So this is the data set we are going to use. Let's see how many observations we have. We have 248 observations on 8 variables, and one of the variables was just case, so 1 output and 7 inputs. And we are going to use neural net function. So the function that you can use to for backpropagation neural networks and many other algorithms here is called neural net. So that's type of perceptron. You can use it for perceptron neural networks. So let's see what it does. It has a lot of components. That's a very flexible function that have been developed. Some of the most important things you're going to use, of course, is what your inputs and outputs here, data. Here you introduce how many hidden layers you want to have, and within each hidden layers how many nodes you want to have, or how many synapses you want to have. For example, if you just write hidden layer is C of 3, 2, 1, that means it has 3 layers. The first layer has 3 nodes, the second layer has 2 nodes, and the last one is 1 node. As I explained in my earlier lectures, you usually only have 2 hidden layers. You can have as many, you can have any number of nodes in each hidden layer, but you usually have 2 of them. 3, I haven't seen any application that uses 3 hidden layers. So if you just write 1 or 2 or 3 here, that means it only have 1 hidden layer with that many nodes. So you have a bunch of other variables as well. So let me emphasize of the most important ones. For example, activation function by default is logistic, but you can set it to tangent, hyperbolic tangent. It's TANH. Or the error function you use can be SSE or CE. SSE stands for sum square error. CE stands for it's an entropy model. So CE. Then I forgot what C stands for. E is entropy. So that is okay. Anyhow, C, you can use CE or SSE. If you want your output to be simple linear case, then you set it to true. But if you want an activation function be run on it, you should set it to true, to false. What I mean is that for classification, you need to set it to false, specifically if you use just logistic regression. So for classification, set linear output to false. If you have a regression model, when you have a quantitative outcome, set it to false. The other interesting variable that you can play with are thresholds, and you can also set the name of the algorithm. In default, the algorithm it uses is resilient backpropagation, and that is rprop plus. But you can use simple backpropagation or modified globally convergent algorithms, many other types. Also, you can say how many steps you want it to go, how many iterations you want to have. You can set it or not. So it's a very flexible function. You can do almost anything that you want with this function. So let's get back to our original data set. In our original data set, inferred, we want to predict if, based on different variables, the inputs, whether you have an infertile case or not an infertile case. So our output is a categorical variable, which is case. It can be only 0 and 1. And we want to regress it on age, parity, induced, spontaneous. These are the 4 variables that were there. As I showed you, there are 7 variables there. So we just use these 4. You can use any number of variables, by the way. There's nothing wrong with that. So the data you have to introduce the data name. The data is the data frame known to R, inferred. You have to introduce how many hidden layers you want. We are using 2 here. Usually a square root of n, where n is number of outputs. N is number of inputs. Here we have 4 inputs. Usually a square root of n is a good hidden layer, but we have to run cross-validation to choose the best hidden layer. Then with the model we want to say, we can use either sum square error or C. And since we are dealing with a categorical variable, we set that to false, because the output is just not a linear, it's a logistic one. So you just wanted to put it in the logistic function to give you the probabilities, which is between 0 and 1. So let's run it and see what will happen. Usually it takes a relatively long time to run, specifically because we're just using rprop plus. That's the name of the activation function, and that is resilient backpropagation function. It usually takes a while to converge. And as we will see later, it's way better the backpropagation. So if you have a choice, you just use rprop plus. If we want to change the algorithm, write algorithm equal to whatever name you're comfortable with. So let's, we're done. Okay, so we have just finished our convergence. We have the model NN. So now let's see what is inside NN. NN is a model that used or data and use hidden layers and so on and so forth. Let's look at the results we get. Oh, there's something wrong with my layer. Let me see what is wrong with it. It's weird. It shouldn't, something that shouldn't have happened. So the algorithm gave me a warning message, said we didn't converge. Okay, now it didn't give me. Okay, so because since you're just using random weights, it's possible that sometimes you do not converge to the place you want to converge. So run it again. So now it converged. It apparently converged. So let's see what we have in NN. Okay, now we can see the neural network that we have converged to the optimal solution in its opinion, and has this much error, 120 cross. Okay, C stands for cross entropy error. And let's plot it. So when you plot it, you can see the overall picture of your neural network. So let me, okay, full screen it. Okay. So we had four inputs: age, parity, induced, and then spontaneous. These were our inputs. We had two hidden layers and one output, which was case. This one stands for your intercept, your constant. So anytime you're dealing with inputs, one of your inputs is just constant. If you do not have any input, the outcome will be close to average. So because of this constant, and you should have this constant in any layer, even in later layers. So basically, it gives you the weights between within weights from one neuron to another one, and you can see the summary of the weights here. So let me close that. Okay. So if you want to look at the matrix of weights, you can do it easily. You can either just refer to it as weights. So these are the weights of our first stage. As you can see, any neuron is connected to two hidden layer neurons. That's why you see two inputs. For example, 120 is this layer to this one, and negative 5.44 is just here. So you can see anything you see here. Also, we have another connection here from hidden layers and our constant to our output. And as you can see the weights here. You can also look at it in another way. You just write resulted matrix. It gives you all of these weights in a different way. So it's basically the same thing, but it's more organized this way. Say, okay, for example, intercept to case. That is intercept to case. Spontaneous to hidden layer 1. So spontaneous to hidden layer 1. That is the output. We have negative 47, as you can see. So it's more convenient to just use your result matrix this way. You can also look at the covariant here, and you can use the actual. You can also look at the actual output. So these are our inputs. These are covariant inputs for all of those four variables we had. These are input vector, and here we have our output, the actual output. We had some controls, which are those zeros, and some actual infertility cases. So if you want to see what was the outcome of our model, what is the prediction of our model for these inputs, the four variable input we have, you can use result 1 this way. So NN was the name of our model. So NN dollar sign net result 1. That corresponds to the value you have. So you shall expect to get numbers between 0 and 1, not necessarily 0, not necessarily 1. They're numbers between 0 and 1. These are the outcomes of logistic function. So let's look at the outcomes we have for all of our observations. We can see that, for example, for 197th observation, it predicts with probability 12.8% case is 0. 12.8% the case is 1, so it's most likely that is 0. So as we learned in earlier courses, when you use logistic function, you can just compare it with 50% chance. If it's more than 50%, we assign it to one of the categories. If it's less than 50%, we assign it to the default category. So here we use if else to just check if these results is more than 50%. If they are, we assign 1 to it. If it's not, we assign 0 to it. So n and 1 would be the outcomes in correspondence to the probabilities that we observed. Now, so n and 1 now are just a bunch of zeros and 1. If you want to see how much misclassification error you have to see how many cases our predictions, which are n and 1, were different from our real inputs, real outputs. Our real outputs were inferred case, the case part of the inferred data, And our predictions are n and 1. So let's see how many times they're not equal and take an average of it. And let's see how much error we make. So we can see we have, by this method, we're making around 22% error. And by the way, if you run that neural network function again and again and again, you may get different numbers here because of the random weights at the beginning that we explained in the earlier lectures. And let's look at if you want to look at the actual outcomes and what you predict side by side, you could just bind them together and see how they look like. And as you can see, it look like, for example, for our 180-second observation, in reality, the case was control, but you predicted an actual case. But in 183rd observation, you predicted correctly, and so on and so forth. Or for example, in 21st observation, it was actually a case, and you predicted a case, which is a very good job. So now let's play with different components of this neural network model, and it's pretty easy. I just put it here so that you see how we can play around with it. So again, you use neural net. What I want to do is, instead of using the default propagation method, I just want to use the actual backpropagation, the classical backpropagation method. So my formula is the same. I just want to regress case on everything else. You can just write formula or not. It depends on you. The data is the same. We use same hidden layer. You can set your learning rate to any number you're comfortable. As we discussed earlier, the larger learning rates will result in faster convergence, less precision. Lower learning rates take a little bit while, but that's the probability of overfit. The algorithm we use is backpropagation, and since let's stop with cross entropy, and linear output should be false as well, because we are again dealing with classification problem. We are not dealing with regression models. So let's run it. Usually backpropagations with such a large learning rate should converge to the actual outputs, to local minima very fast. And it did. So let's see what is NNBP. So NNBP just made 158 error, and it converged in 5 steps. So let's compare it with NN so that you see which one is doing better. NN, which was our original one, which used our resilient backpropagation method, because we didn't define any algorithm here, created 120 error. In backpropagation, it created 158, but that one converged to to its minimum solution in 225, more than 25,000 steps. That was why it took us so large to get there. But here it converged in 5. So as we can see, backpropagation doesn't outperform the actual resilient backpropagation method we have. So now sometimes you want to just make some predictions. So if you want to do predictions, or for example you want to use it for cross-validation, you set aside some test data and you just want to use your trained neural network for predictions of your test sets. What you need to do is to put your inputs in a matrix, in a vector, and then define how many observations you had. So so the covariance will be our inputs. You have to introduce it to it, and let's see. We have 4 inputs: age, parity, induced, spontaneous. So let's say our first observation we want to predict for is for a case that has age 22. Parity is 1. Didn't have induced or spontaneous action before. I think infertility action before. The second case is also 22 years old. Parity is 1. Induced. It had induced for abortion before, but no spontaneous abortion. Our third case is 22 years old, had parity is 1, induced abortion was not not there, but spontaneous abortion was there. In the last case, has age 22, parity was 1, it was both induced and a spontaneous abortion. So you set by row by true so that you tell it, okay, that's a vector you're looking after. And if you do that, you have to introduce number of columns. That is number of these are number of actual inputs you have, actual number of variables you have. So this is for our inputs. And now you say, okay, this is my model, and you just put it in a function called compute. So compute has two parts. The first part is your model. The model we're going to use is NN, our original model that we use for our neural networks. That is NN, so that's our original model. And then you have to introduce your inputs. So here I just want to make a prediction for 4 of the cases. And I set by to true, and I say, okay, we have 4 variables. So that way it knows that we are working with 4 observations. Why? Because we have 4 variables and 16 observations. 16 divided by 4 is 14. Is 4 observations. So let's run it. And now let's look at the net result portion of new outputs. So let's interpret these results. These results say that, okay, for the person who was 22 years old, and had I forgot what was, okay, had parity 1, and it didn't have any induced or spontaneous abortion, the probability of infertility is 13%. So you will categorize her as not an infertile case. However, for the person who is 22 years old, has had one parity and had one and the case for a spontaneous abortion was apparent, and also induced abortion, your prediction for infertility is 84%. So that's how you just use your model for prediction, and you can use it for cross-validation. I haven't found a good package to do cross-validation based on this yet, and as soon as I do, I will post it online. And even if I cannot find such a case, I will most likely write my own code so that you can just start playing with that. And last thing that I want to, penultimate thing I want to discuss is how do we build up confidence intervals for our weight matrix. So these weights. It's very easy actually in this case. You just the command you use is confidence interval. You need to use your model and the significance level you want. So the confidence interval is just 1 minus alpha. So if you set alpha to 5% like this, confidence interval will be 95%. So let's run it and look at CI. It builds up a lower and upper bound confidence interval for all of these numbers. For example, for this, so our first input is 118. So that means the lower bound of confidence interval for that 120.29 is 118. The upper bound is 122. Let's look at this part. That says the lower bound for this negative 5.44 is negative 10. The upper bound is negative 0.2. So as you can see, the average of the two is negative 5.44. And so does for everything. Yeah, so let's for example, for the sake of example, let's focus on the confidence interval for this weight. That is in our second layer, so that's here. So the lower bound for that is negative 5.27, negative 5.27. The upper bound is negative 0.64. One of the things I want you to notice is these weights for age. So the age. So as you can see, this age has is between 0.445 to 1.22. If you just compare it with the magnitude of other results we have here is relatively small. And if you just look at the second weight matrix for age, it's between negative 0.5 and 0.32. So as you can see, 0 is within this confidence interval. Usually when such a thing happens for one of our variables, it's usually not significant. And one of the ways you can just visualize the result and the effect of each variable on our outputs is just by simply graphing it, so visualizing the result. So what I want to do now is to visualize the effect of each variable for our case. So let's just divide our output, the output display into 4 parts, 2 by 2, and from our earlier lectures, you know how to do it is MF row C22 in par. So we are going to plot our model with this selected covariate. Here is selected input age, and I want to show it between two values. We also want to show that, oh, figure margin too large. Okay, so let me do that. Okay. Okay. Maybe because I zoomed in so much. Okay. So to do that, I need to zoom out a little bit. Zoom out. Once again, zoom out. Zoom out. Okay. So it should be fine now. Okay. So if such a thing happens for your margins, you need to zoom out. So let's zoom in and see how these plots look like and what do they infer, what they do infer. So look at age. As you can see, for age, the effect of age and the output is usually 0. So that will suggest age is not such an important factor here. So if you really want to have a neural network that works, we should exclude age from it. But as you can see, for parity, spontaneous, and induced abortion cases, you see so much variability here, and that's a very good sign. That means you could actually see the effect of these variables on the output, specifically for these two. Yeah, you can see it for parity as well. So the lesson we get here is that if you just draw your results and see one of your variables is not that effective, that only means that if it is scattered around 0 all the time, means this variable didn't have that much of an effect. And we saw that earlier too when we built up the confidence intervals for the weights. So that was the course today about using perceptron neural networks, applying backpropagation methods and some variants of that. One of the things we just learned is that if we want to use it for classification, we should set our linear output to false. Otherwise, it's true. And it's relatively easy to play with neural network functions using neuralnet library, and I hope you had fun with it. That's basically how our mind works, neural networks, and it's very cool to program it in a very naive way. Our neurons in our head works in a parallel fashion. This is more sequential, but even so, I feel it's a very interesting topic, and I hope you enjoyed that. Thank you so much.